Throughout this course, we've examined a wide array of engineered systems, which are composed almost entirely of materials obtained from just two sources. First, most engineering materials are extracted from the Earth's crust by mining, quarrying, and drilling. These include metals, petroleum-based products like plastics, lubricants, and asphalt, the constituents of concrete, brick, ceramics, and gypsum, the silicon used for electronic components and glass, soil, an integral component of foundations, earth dams, and tunnels, and stone, as you see in this granite quarry. And second, we obtain several important engineering materials from plants, including wood, natural rubber, and various resins. But sooner or later, all of the devices and structures made from these materials break, become obsolete, or are no longer deemed useful, and they're discarded. Thus is the cycle completed, as materials drawn from the Earth are returned to the Earth in the form of worn-out consumer goods, used construction materials, expendable products, packaging, junked cars, broken parts, and all manner of other formerly useful things. In the US, we generate about 4.5 pounds of solid waste per person per day, nearly a ton per person per year. Aggregated across the entire population, the numbers are staggering. For example, we use 80 billion aluminum cans per year, 22 billion plastic bottles per year, and paper and wood products amounting to 2 billion trees per year. During this lecture, we'll examine the three principal methods of dealing with all this waste: disposal in a landfill, incineration, and recycling. Along the way, we'll see that the process of solid waste disposal is significantly more challenging, and the results are somewhat less satisfactory than, for example, the wastewater disposal process that we discussed in an earlier lecture. This insight will set the stage for the final lecture of this course, when we'll look at sustainability and its implications for the future of everyday engineering. Now, when I was a kid, my family hauled all of our trash to the town dump, and it looked pretty much like this. Today, the trash is now known as municipal solid waste, and the dump is now called a sanitary landfill. Now, in practice, the trash hasn't really changed all that much, but the disposal facility is as different as its new name might suggest. Our old town dump was just a large plot of land set aside for the open disposal of garbage. A modern sanitary landfill is a technological system designed by environmental engineers to return solid waste to the earth in a way that maximizes the use of available land and minimizes harm to the environment. When organic material is placed in a landfill, it begins to decompose through the action of bacteria and other microorganisms. When rainwater percolates down through this material, the moisture promotes decomposition, and in the process, the water also becomes contaminated with dissolved organic matter, heavy metals, and a variety of other nasty substances. The resulting toxic acidic liquid is called leachate, and the most important objective of a sanitary landfill design is to contain, collect, and remove the leachate to prevent contamination of the local groundwater, streams, and rivers. Now, decomposition of organic material also generates a byproduct known as landfill gas, a mixture of methane, carbon dioxide, and small amounts of nitrogen, oxygen, and other gases. Landfill gas is explosive, and its two principal components, methane and CO2, are greenhouse gases. Thus, a secondary objective of landfill design is to detect, capture, and dispose of dangerous accumulations of landfill gas. Construction of a typical modern landfill begins with excavation of a broad, flat-bottomed pit, roughly 25 feet deep. The excavated soil is stockpiled so it can be used for cover later. Next, the bottom and sides of the pit are sealed, first with a layer of compacted clay, and then with a waterproof geomembrane. Now, clay is used for its impermeability, a characteristic we first noted in our discussion of earth dams in an earlier lecture. A geomembrane is a strong, flexible, puncture-resistant plastic sheet, usually less than 1/10 of an inch thick, and with very low permeability. The clay liner and geomembrane serve as a belt and suspenders liner to prevent leachate from entering the soil beneath the landfill. A thick layer of gravel is placed over the membrane, both to protect it and to allow for the free flow of leachate. Embedded within this layer is the leachate collection system, a network of perforated plastic pipes that capture any leachate entering the gravel bed from above and channel it down to low points called sumps. Within each sump is a pump that transports any accumulated leachate out of the landfill for disposal. We'll look at the process of leachate disposal in a few minutes. This leachate collection system is absolutely essential because no geomembrane is perfectly impermeable. Without a well-functioning collection system, leachate would accumulate on the membrane and would eventually seep through it and contaminate the surrounding soil. Now, above the gravel layer is a durable synthetic fabric called a geotextile, covered by a protective layer of sand or other soil. Unlike a geomembrane, a geotextile is intended to be permeable. It serves as a filter, allowing the leachate to pass through, but preventing the soil and other solid material from entering the gravel bed and clogging up the leachate collection system. With this uppermost layer of soil in place, the facility is ready for operation. In the typical landfill, garbage trucks deposit their loads at the base of a sloped embankment called the working face. Bulldozers and rollers are then used to distribute and compact this trash along that slope. Each day's deposit of trash is confined to a rectangular area called a cell, as shown here. The size of a cell can vary significantly depending on the amount of trash produced by the local municipality. In general, the goal is to keep the cell's footprint as small as possible for more efficient management of available landfill space. By the end of each day, the compacted trash in this cell will be about 4 to 8 feet thick, and then it'll be completely covered with 6 to 12 inches of soil and compacted once again. This application of soil, called daily cover, keeps the trash contained, it reduces water infiltration, controls odors, and discourages insects, vermin, and other scavengers from taking up residence. And the next day, this process starts all over again with the creation of a new cell. Once the landfill is in operation, control of leachate is of paramount concern. 6 separate but interrelated systems are devoted to this task. The first is the leachate collection system, which we've already seen. Any rainwater that penetrates down through the daily cover percolates down through layers of compacted trash and eventually reaches the bottom of the system as contaminated leachate, where it's captured by those perforated plastic pipes, directed down to the sump, and then pumped out. At some landfills, the destination is a holding tank or pond, which is used to store the leachate temporarily until it can be trucked away to a wastewater treatment facility. But many larger landfills actually have a treatment facility right there on site. Second, because these wastewater treatment systems typically aren't equipped to handle chemicals contained in hazardous waste, most municipalities impose a strict ban on the disposal of hazardous wastes in standard landfills. And in case you were wondering, yes, we have plenty of opportunities to produce hazardous waste in our own homes. The U.S. Environmental Protection Agency classifies such common household items as paints, chemical cleaners, motor oil, batteries, and pesticides as hazardous. If these substances are contained in the trash stream, they'll eventually find their way into the leachate. They won't be entirely removed at the wastewater treatment facility, and thus they'll be discharged into a river or stream where they're quite likely to damage ecosystems and water supplies somewhere down the line. Third, the amount of leachate production can be limited by minimizing the amount of rainwater percolating into the soil in the first place. Thus, a well-designed landfill incorporates an extensive stormwater management system with drainage pipes and ditches for capturing storm runoff and carrying it into a stormwater collection pond for temporary storage. The water in the pond must be tested and found to be free of leachate chemicals before it can be released into the wild. Another potential source of leachate is liquid contained within the trash itself. So most municipalities forbid the disposal of any liquids in landfills. And many incorporate a system for inspecting incoming loads of trash to ensure that they contain no liquids. Fifth, well-managed landfills include a tire washing facility at which the garbage truck's tires are cleaned to prevent them from depositing leachate on public roads, where it would eventually be washed into the public storm drainage system. And finally, groundwater monitoring wells are installed around the perimeter of the landfill, as you can see here. These wells facilitate routine, direct sampling of the groundwater to check for the presence of contamination. If any leachate chemicals are detected in the groundwater, it means that either the collection system or the containment system, that is, the membrane and clay layer, has failed. In either case, immediate corrective action is warranted. Now, once daily cells have been stacked all the way up to the original grade level, this section of the landfill is capped. The cap typically consists of a layer of compacted clay, then a geomembrane sealer, a drainage layer of gravel or sand, and then a protective layer of soil. Topsoil is added to the top of the cap, and then vegetation is planted to stabilize the soil and prevent erosion. Though trees or shrubs with deep roots aren't allowed because the roots might extend downward and puncture the membrane. The cap is normally crowned like this, so as much stormwater as possible will run off rather than percolating down into the landfill. The overall intent of the cap is to minimize water infiltration and thus to minimize the production of leachate. With the cap in place, the conditions are ripe for the dangerous buildup of methane underground, and so a gas collection system is typically installed at this time. These pipes constitute the upper end of just such a system. Indeed, in the US, the Clean Air Act amendments of 1996 require the systematic collection and control of landfill gas, not just for safety reasons, but also because methane is considered to be an extremely potent contributor to climate change, at least 25 times more potent than CO2. Until relatively recently, this requirement was usually met by piping the gas to a flare where it was simply burned off. But today, an increasing number of landfills are incorporating recovery systems that put landfill gas to more productive use by any of three methods: either burning the gas in a nearby industrial boiler to produce hot water, or using it to generate electricity by powering an on-site gas turbine or steam turbine that drives a generator, or processing the gas for sale to the local gas company. In the US today, some 600 landfills, about 30% of the total, incorporate these sorts of systems. Interestingly, several major environmental groups strongly oppose these gas recovery projects. Now, on one hand, this position seems entirely illogical because the only feasible alternative to gas recovery is disposal by burning. Thus, the gas will be burned, whether the energy is used productively or not. And if the energy embodied in landfill gas is used productively, then less energy will need to be produced elsewhere. But the opponents argue that landfill gas to energy projects don't really achieve the overarching goal of reducing methane emissions. One reason is that controlled flares are generally more effective at oxidizing methane than are the engines used to generate power. But more importantly, once a gas-to-energy system is in place, the owner's economic incentive is to maximize gas production in order to maximize power output. This is typically accomplished by delaying the installation of the landfill cap so that more water will infiltrate into the system. More water means more decomposition, which means more methane. But because most gas collection systems capture only a small fraction of the methane produced, the net effect is a significant increase in emissions. As an alternative, these groups advocate better waste management practices aimed at reducing methane generation by reducing the disposal of decomposable organic waste in landfills. I'll let you be the judge of which argument is more compelling. But for the purposes of this course, this controversy very nicely illustrates three broader points. First, that issues surrounding the environmental impact of technology can be quite complex. Second, that unambiguously correct responses to these issues are rarely available. And third, that taking a well-reasoned position on these issues requires some understanding of the associated technology. As further evidence of the inherent ambiguity in environmental protection, it's worth noting that the total number of landfills in the US, roughly 2,000, has declined by over 75% in the past 3 decades, as increasingly stringent environmental regulations governing their operation have tended to favor smaller numbers of larger landfills. The unintended consequence of this trend is that the trucks hauling solid waste from your curbside to your landfill now must travel significantly farther, thus burning more fossil fuel and contributing considerably more to both air pollution and carbon emissions. Major cities like New York that ship their garbage to neighboring states have made this problem even worse. Sometimes it does seem that no environmental good deed goes unpunished. When a landfill is completely filled, it's fully capped and closed. And while the surface of the land might be converted to other uses, what's happening below the surface, the continued production of leachate and landfill gas, must typically be monitored for at least 30 years afterward. The reason, which you've probably surmised from our earlier discussion, is that well-designed landfills limit decomposition rather than promoting it, by preventing water and air from coming into contact with the buried trash to the greatest extent possible. The fact that this design concept works has been dramatically demonstrated by a research project led by Professor William Rathje at the University of Arizona back in 1973, called the Tucson Garbage Project. Its main goal was primarily anthropological rather than technological. Rathje and his team wanted to explore a rather fascinating hypothesis, that we can understand more about the lives people lead from what they throw away than from what they report about themselves. But in the course of conducting archaeological digs to determine the contents of landfills, Rathje was quite surprised to find nominally biodegradable trash, newspapers, lawn waste, and even perishable food items that had hardly decomposed at all after several decades. He concluded that, contrary to popular perception, the landfill is more a mummifier of trash than a decomposer of trash. Now, to me, this revelation is both reassuring and worrisome. It's reassuring because this vision of slow, controlled decomposition in a well-engineered sanitary landfill represents such a striking improvement over the town dump I knew as a kid. But it's also worrisome because it means that the hundreds of millions of tons of garbage we deposit in landfills every year aren't going anywhere anytime soon. Now, one of our 2 principal alternatives to the landfill is incineration. In many ways, the concept of incineration seems ideal. Burning waste reduces its weight by 80% and its volume by 95%, and the resulting heat can be used to generate electrical power. The byproduct of incineration is a small quantity of inert ash that takes up a tiny fraction of the landfill space that would have been occupied by the original material. Incineration largely eliminates the problem of methane emissions from landfills, and paradoxically, the use of incineration has been found to actually improve rates of recycling, primarily because metals can be separated from other materials more easily by burning than by mechanical disassembly. Yet, despite these desirable features, less than 15% of municipal solid waste in the US is incinerated today, and this percentage is actually on the decline. Why? Well, there are 3 main reasons. Most importantly, the emissions caused by incineration are highly toxic. These can be controlled to some extent by pollution control devices called baghouse filters. But these devices are expensive, and safely disposing of the toxic fly ash they capture can be a significant challenge. Second, incineration also produces substantial CO2 emissions. And third, from the perspective of power production, municipal solid waste is a very poor quality fuel. Because the waste stream is so highly variable, considerable sorting and mixing is essential before it can be burned. Thus, this process can only be partially automated, and so it's expensive. And variability in the fuel also results in highly variable heat and power output. In comparison with the controlled combustion of coal, oil, or gas in a furnace, the combustion of trash is less complete, takes longer, and it produces less heat. Thus, a trash-fueled power station produces significantly less electrical power and requires significantly more expensive pollution controls than an equivalent conventional power plant. Now, I should note that these challenges aren't insurmountable. Japan and several European countries have been quite successful in implementing large-scale, environmentally responsible trash-to-power projects. Denmark, in particular, produces about 5% of its electrical power and over 10% of its domestic heat through waste incineration. In the US, however, this approach to solid waste disposal is evidently not a growth industry. The third approach is recycling, the process of salvaging waste and transforming it back into usable materials. Recyclable materials include, but are certainly not limited to, metals, glass, plastic, paper, textiles, and electronics. These multicolored recycling bins at curbside have become a fact of life in modern society. In the US today, roughly 30% of municipal solid waste is recycled, over triple the percentage from 1980. Yet, the viability and effectiveness of recycling remains highly dependent on the specific materials being recycled. Recycling aluminum is amazingly efficient. The process requires only about 5% of the energy consumed in producing aluminum from raw bauxite ore. So there's a strong economic incentive for manufacturers to use recycled material. And there's no limit to the number of times aluminum can be melted down and reused. Recycling steel isn't quite as efficient. Cooking up a batch of steel from scrap takes about 40% as much energy as producing it from iron ore. But that's still a substantial saving in an energy-intensive process like steelmaking. As a result, in the US today, over 95% of structural steel is recycled, and several major producers now manufacture 100% of their steel from scrap. Glass is recycled by simply crushing and remelting it, a relatively efficient process that consumes only about 70% of the energy required to make glass from scratch. But in this case, there's a new twist. Because glass retains its color after recycling, manufacturing bottles from recycled glass requires that the glass be strictly segregated by color, brown, green, or clear. This need for sorting imposes an additional cost on the recycling process, and it can also cause some interesting supply and demand challenges. For example, the British are the world's largest importers of wine, primarily because their domestic wine industry is relatively small. They also have a very robust spirits industry, and they export a substantial fraction of their total production. Consequently, their recycling system is burdened with a mountain of unwanted green glass and a shortage of clear glass. Now, in recent years, this limitation has been eased by the development of new recycled glass applications that don't require segregation by color. For example, crushed glass is now being used for abrasives and for aggregate for countertops and concrete. Purists categorize these sorts of applications as downcycling rather than recycling, because the quality of the reconstituted product is downgraded from the original. Now, this might sound like a merely semantic distinction, but it's actually quite substantive. Glass, for example, is infinitely recyclable. There's no limit to the number of times it can be melted and reformed. But once it's embedded in a countertop or sidewalk, its next destination is almost certainly a landfill. Now, of all the major recycled products, plastic is probably the most problematic, in part because there are so many different types of plastics, but especially because very few of them can be remelted back to their original pure polymer form. Thus, most plastic is downcycled rather than recycled. Recyclable plastic is generally marked with a resin identification code, that familiar number inside a triangle logo that identifies the type of polymer used in its manufacture. Plastic with code 1 is polyethylene terephthalate, or PET, commonly found in beverage bottles and various forms of packaging. Now, PET is most commonly recycled into polyester fiber for fabric and carpeting. Code 2 is high-density polyethylene, or HDPE, used in applications requiring high strength, like geomembranes, hard hats, house wrap, and vehicle fuel tanks. And it's typically recycled as bottles, plastic lumber, furniture, and quite appropriately, recycling bins. The standard resin identification codes continue all the way up to 7, though in many US municipalities, only PET and HDPE, that is, only codes 1 and 2, are collected in curbside recycling programs. The result is a lot of public confusion about what can and cannot be recycled. For these reasons, less than 10% of our discarded plastics are actually recycled. Comparing the recycling rates of, say, steel and plastic illustrates two fundamental challenges inherent in recycling. Let's call them the sorting problem and the market problem. In the manufacture of consumer goods, as pure raw materials are incorporated into useful products, these materials become intermingled, interconnected, and dispersed. In recycling, these materials must be classified, segregated, and then amassed in quantities large enough to make their reuse economically viable. Sorting is often done in part by consumers prior to collection, but much additional sorting is always required at a central processing facility. In cases where sorting is difficult or confusing, recycling rates tend to suffer, and the cost of recycling increases. One reason why such a high proportion of steel is recycled is that ferrous metals are so easily culled from a trash stream with large magnets. One reason why plastic recycling rates are so low is that we often can't even figure out what's recyclable and what isn't in any given municipality. Now, in recent years, the economics of sorting have changed, as some very impressive new automated sorting technologies have come online. These include optical sorting machines that can distinguish the colors of glass, and spectroscopic scanners that can distinguish between different types of paper and plastic based on their absorbed wavelengths. It remains to be seen whether the benefits of these technologies will justify their costs, particularly for small-scale recycling operations. But the larger issue is the market problem. The principal reason why steel recycling rates are so high is that scrap steel is inherently valuable. Manufacturers can make steel products significantly more cheaply from scrap than from ore, so they buy up every piece of scrap they can find. Plastic has inherently low value, and the cost of transforming used plastic into a useful material is relatively high in comparison with manufacturing plastic resin from petroleum. Though I should note that this comparison tends to vary wildly, depending on which source you read, and depending on the current price of oil. But in any case, the market for used plastic is significantly more limited than that of scrap steel. The reason that so many municipalities only accept resin codes 1 and 2 is that so few manufacturers are willing to buy the other types. Professor Michael Munger, a Duke University economist who has studied and written on the economics of recycling, sums up the market problem quite succinctly when he writes, "If someone is willing to pay you money for something, it's a resource. If you have to pay them to take it away, it's trash." Today, much of our plastic and other materials like construction debris and automobile tires are still trash. Now, on the other hand, there's a problem with evaluating the merits of recycling in purely economic terms. Such analyses typically don't account for externalities, costs and benefits that accrue to people who aren't directly involved in the economic transaction. In this case, that's the transaction between the municipalities and the manufacturers that buy the recycled materials. The externalities relevant to recycling include reduced energy consumption, reduced consumption of natural resources, decreased air pollution resulting from less combustion during manufacturing, reduced demand for landfill space, and reduced potential for air and water pollution from landfills. These represent important benefits to society at large, benefits that most people are willing to pay for. And indeed, in a way, we do pay for these benefits by subsidizing recycling operations with our tax dollars. The problem is that decisions about recycling are sometimes driven more by emotion and by a moral commitment to recycling than by rationality. We see this, for example, in communities that expend substantial resources on the curbside recycling of yard waste, even when there's little practical use for and no market for all this material. Michael Munger, the Duke economist, wrote about one such program in Durham, North Carolina. In this case, yard waste, with essentially no economic value, was accumulated in a huge compost pile at considerable cost, until the pile caught fire and took weeks to extinguish. Ultimately, this essentially worthless material was shipped off to a landfill in Virginia because North Carolina state law prohibited it from being dumped locally, and the municipality couldn't figure out anything else to do with it. In dealing with these sorts of issues, what's really needed is a broader, more rational approach to managing the materials we acquire, use, and discard. Just such an approach is embodied in the concept of sustainability, a big idea to which we shall turn in our final lecture. For most of this course, I focused primarily on everyday engineering as a powerful means of enhancing human quality of life, and as a testament to human ingenuity and industry. But while I fervently believe in the enduring value of the engineering enterprise, it would be irresponsible to ignore or understate its downside. From the dawn of the industrial era to today, advancement in technological development has gone hand in glove with an ever-increasing consumption of natural resources and significant degradation of our environment. The numbers are so large that they're difficult to comprehend. Today, in the US alone, we'll consume about 800 million gallons of oil in one day. Today, we'll burn over 5 billion pounds of coal, mostly for the generation of electric power. Today, we'll consume over 1 billion gallons of water, and today we'll dispose of over 1 billion pounds of solid waste. Now, in previous lectures, we've explored various approaches to conserving energy, reducing pollution, and reducing solid waste disposal through recycling. Yet, effective as these measures might be, they haven't yet had the large-scale impact we need, largely because each addresses one particular aspect of the problem in isolation. What's needed is a more holistic approach, and indeed, just such an approach is currently taking hold. It's called Design for Sustainability, or Sustainable Engineering, and in my view, it's the most important trend in the world of engineering and technology today. Sustainable engineering is engineering that meets the needs of the present without compromising the ability of future generations to meet their own needs. At the heart of this concept is a recognition that the Earth's resources are finite. Every ton of iron or barrel of oil we extract from the Earth depletes that finite supply. And logically, if we continue to do so, then that supply must eventually be exhausted. With this concept in mind, one might logically conclude that true sustainability can only be achieved by extracting zero resources from the Earth. That is, by generating 100% of our energy from renewable sources and obtaining 100% of the materials we need for new products from recycling. Based on this definition, true sustainability is almost certainly impossible, because the quantity of materials needed for new products inevitably exceeds the quantity that can possibly be recovered from recycling. Nonetheless, even if this idealized vision of sustainability isn't wholly achievable, we can certainly do a lot better than we're doing today. The most fundamental premise of sustainable engineering is that we must look holistically at the entire life cycle of the products we develop. This graphic illustrates the traditional non-sustainable approach to product development, a simple linear process that starts with extraction of raw materials and ends with disposal of product when it's reached the end of its useful life. The perfectly sustainable but unachievable alternative looks like this, with production, use, and recovery occurring in an infinite cycle. And here's the pragmatic middle ground, a reasonably sustainable approach in which we seek to repeat the production, use, recovery cycle as many times as possible, but acknowledge that some external sourcing and disposal of material resources will usually be required at the beginning and end of a product life cycle. Clearly, the most important difference between the traditional and sustainable models of product development is the recovery phase. But this doesn't mean that sustainability is only considered during the recovery phase. Indeed, the most important aspect of this model is that sustainability must guide the implementation of all 5 phases. To illustrate this point, let's consider this model in the context of some everyday technologies we've discussed throughout the course. In residential construction, for example, the sustainable sourcing of materials might include the use of engineered lumber like oriented strand board and plastic lumber rather than conventional sawed lumber, because engineered products use wood fiber far more efficiently. It might include the use of roof trusses rather than rafters, because trusses are more structurally efficient and thus use significantly less lumber. Or the use of cellulose insulation, which is manufactured from recycled newsprint and actually has an R value comparable to fiberglass batting. Or the use of metal roofing rather than asphalt shingles, because metal roofing lasts longer and is more easily recycled. In the US alone, 11 million tons of waste asphalt shingles are dumped into landfills every year, while nearly 100% of waste steel goes back into the furnace to manufacture new steel products. Sustainable sourcing also entails using locally produced materials wherever possible, because shipping materials halfway around the globe consume substantially more energy and, in particular, more fossil fuels. The concept of sustainable production is best represented by the growing number of companies that are building smart factories, facilities employing such technologies as on-site renewable power generation, low-energy lighting, rainwater harvesting, water recycling, and on-site wastewater treatment, with the resulting methane gas captured and used as fuel. These factories are able to manufacture useful products with drastic reductions in energy consumption and dramatically less environmental impact. Sustainable production can also be enhanced through the use of advanced engineering processes like 3D computer modeling and simulation, which significantly reduce the number of physical prototypes that need to be fabricated during the design and testing of new products. Sustainable use is exemplified by all the residential energy efficiency measures we discussed in our lectures on this subject. Use of enhanced insulation and air sealing methods, energy efficient heating and air conditioning equipment, and local renewable power generation, all of which reduce the consumption of energy during the entire useful life of a house. 2 years ago, my wife and I bought an older home built in 1970. Sadly, it isn't very energy efficient, in part because it's heated by an electric heat pump that, as you know, doesn't perform very well in extreme cold. Thanks to a particularly brutal winter last year, we consumed about 30,000 kilowatt hours of electricity. But with reasonable attention to energy efficiency, a modern home of equivalent size located in the same region should be able to cut that number in half, quite easily. Assuming this hypothetical new house lasts for 80 years, the total energy savings over its lifespan would be equivalent to 650 tons of coal, or 2,200 barrels of petroleum. That's the total for one house, a dramatic illustration of the long-term benefits of modest investments in energy efficiency. Next, you might think of sustainable recovery as being synonymous with recycling, but it's actually much broader. This conceptual model depicts a hierarchy of sustainable recovery options that might be taken at the end of a product's useful life. The model suggests that the first priority in sustainable recovery is actually rigorous maintenance to extend the life of the product. If I change my car's engine oil often, I'll prolong its useful life, and thus I'll delay the significantly greater consumption of resources associated with disposal and replacement of the engine or the entire car. Eventually, however, a major component like the transmission, for example, will fail. And I might have to choose to have it refurbished or to replace it with a previously refurbished transmission, which I'll reuse. Both of these options consume considerably less energy and fewer resources than buying a newly manufactured transmission, and thus are preferable from a sustainability perspective. If I must replace a component that can't be refurbished, let's say a broken motor mount, then it should be recycled. And only in cases where recycling isn't possible should the component or the system as a whole be hauled off to a landfill or an incinerator for disposal in an environmentally responsible way. Well, this 5-phase model of sustainable product development is filled with good ideas, but how can they actually be implemented in a comprehensive way? Well, the answer is that sustainable sourcing, production, use, recovery, and disposal must be designed into the product from the outset. Thus, the principal responsibility for sustainability lies with the engineer or architect who has principal responsibility for its design. Your new house won't be oriented to maximize solar gain unless the designer applies passive solar design principles from the start. Your house won't be built with structural insulated panels like this one unless it's specified by the designer. Your new toaster won't be maintainable unless the designer makes better accommodations for disassembly and repair than this. How do I get this apart anyway? And recycling will never be optimized until products and their packaging are purposefully designed with recycling in mind. Note that this package for a kid's toy uses 3 different materials: cardboard, plastic, and steel. Am I really going to pull out these metal grommets and recycle them separately? And who thought it was a good idea to use such complex packaging for a 50-cent pair of kids' scissors? So, if designers are principally responsible for sustainability, how to ensure that they apply sustainable design principles in their work? Well, there are several feasible approaches. One is government action, either legal mandates or incentive programs, and this approach can indeed produce results. For example, in 1991, Germany passed a law that assigned responsibility for the entire life cycle of all packaging to manufacturers. The appeal of this system is that it provides a strong economic incentive for manufacturers to avoid overpackaging and to design packaging that lends itself to efficient recycling. If they don't get it right, they pay the price. As a result, recycling rates in Germany are typically above 60%, about twice that of the US. The success of this particular initiative notwithstanding, today the most important advances in sustainability are happening without government intervention. There are 2 reasons for this very encouraging trend. First, many aspects of sustainability are good for business. It's not unusual for the smart factories I described earlier to use half as much power and water as conventional factories. That sort of reduction is just as beneficial for the bottom line as it is for the environment. Moreover, consumers are demonstrating in increasing numbers that they're willing to support companies that operate sustainably, and they're willing to pay for sustainable products. Second, within the past decade, the engineering community has embraced sustainability as a professional responsibility and as a major focus area for the future. At the most fundamental level, this is not really a change of direction for the engineering profession. The ethical focus of engineering has always been on serving humankind. Remember Kipling's poem, The Sons of Martha, in which the engineer is lauded for simple service, simply given. But today, we've begun to recognize that our obligation to serve extends to future generations as well as our own. The professional community's embrace of sustainability has already resulted in the inclusion of new energy efficiency provisions in building codes, substantial research and development in sustainable design, inclusion of sustainability provisions in professional codes of ethics, and adoption of rigorous sustainability certification programs for individual architects, engineers, and builders, for the materials they use, and for the products of their work. One such certification program is LEED, which stands for Leadership in Energy and Environmental Design, a program initiated by the U.S. Green Building Council in 2000. LEED provides voluntary certification of commercial buildings, schools, healthcare facilities, neighborhood development projects, and private residences. In the LEED certification process, projects are evaluated according to a broad range of sustainability criteria organized into credit categories. Points are awarded in each category, and the point total is used as the basis for assigning one of 4 possible certification levels. The highest, LEED Platinum, then LEED Gold, LEED Silver, and finally LEED Certified. And the LEED credit categories for private homes are worth reviewing, as they clearly reflect the holistic nature of the rating system. The Integrative Process category gives credit for the use of an integrated project team to manage both design and construction. The Location and Transportation category rewards avoidance of sensitive land and access to energy-efficient transportation. The Sustainable Sites category recognizes low-impact stormwater management practices. The Energy and Atmosphere category allocates points to such factors as building orientation, insulation, windows, control of air infiltration, hot water distribution, lighting, and appliances. The Materials and Resources category rates the use of environmentally friendly construction materials and waste management practices. There are also categories for indoor environmental quality, water efficiency, innovation, and regional priority. And despite the entirely voluntary nature of this program, over 50,000 projects have been LEED certified since 2000, and the rate of participation continues to grow. More importantly, LEED certification has become a badge of honor among building owners, architects, and engineers, a very exciting development that can only further the cause of sustainable design. The success of LEED and a host of similar programs is, in my view, cause for great optimism about the future of everyday engineering. I fully expect that every topic we've discussed in this course will be profoundly affected by the sustainability movement over the next few decades. I urge you to watch for these developments and to take the time to learn about them so you'll be an informed user of these new sustainable technologies. And now, I'd like to conclude this lecture and our course with a rather fascinating case study. If you're so inclined, please consider this your final exam. And if not, well, I think you'll still find it quite useful as a vehicle for synthesizing many of the big ideas we've discussed over the past 36 lectures. So let's do this. On August 14th, 2003, just after 4 p.m. Eastern Daylight Time, 8 states in the northeastern U.S. and the Canadian province of Ontario were plunged into darkness by the largest electrical power blackout North America has ever experienced. 55 million people lost power during this blackout. Now, August 14th was a typical hot, humid summer day across the Northeast, and the entire regional power grid was experiencing high loads due to air conditioning demands. In northern Ohio, the epicenter of the blackout, system voltages were running relatively low because of the high power demand, but the situation was neither extraordinary nor unmanageable. That afternoon, a large inter-regional transfer of power was underway from the south-central U.S. to the cities of Detroit, Cleveland, and Toronto, which weren't producing enough power to meet their local demand at that time. Then, at 1:31 p.m., the 600-megawatt East Lake 5 power plant near Cleveland tripped offline when its automatic control system detected an abnormal condition. The grid responded as it should have, by rerouting power from other generating stations to accommodate the East Lake shutdown. But as a result, the loads on several high-voltage transmission lines in the region increased. Now, as you know, power transmission generates heat in the electrical conductor. The resulting temperature increase causes the conductor to expand, and as the line gets longer, its sag increases. Unfortunately, Northern Ohio's regional power utility had failed to prune the trees along its transmission rights of way, and at 3:05 p.m., a 345,000-volt transmission line sagged into a tree, generating a flashover that tripped circuit breakers and disconnected the line. Now, in the grid, electrical current flows along all available paths from generators to loads, governed only by the laws of physics. If one of these paths is lost, the current reallocates itself among the remaining paths. But in the process, the load on these paths increases. Thus, 27 minutes after the first transmission line failed, the reallocated load caused another line to sag into trees and trip offline. At 3:41, yet another one failed, this time because it was loaded 20% beyond its capacity. And within 25 minutes, 16 more overloaded Northern Ohio transmission lines tripped offline in rapid succession. This was the decisive moment in the crisis. According to the subsequent official investigation of the blackout, up to this moment, the regional utility company could still have averted the catastrophe by initiating emergency load shedding in the Cleveland-Akron area. That is, by deliberately cutting power to local consumers to reduce demand on the system. But the utility didn't act because just 2 hours earlier, a seemingly minor software bug had disabled the control room alarm system and no one knew it. Not only did this failure deprive the system operators of critical warnings as the crisis unfolded, the lack of alarms also convinced them to ignore several warning signals from other sources. Now, at 4:06, the last major transmission line in Northern Ohio failed, and that large interregional power transfer rerouted itself onto other paths through Western Michigan, Pennsylvania, New York, and Ontario, as shown here. This huge power surge began tripping transmission lines all along its path at an ever-increasing rate, as more power flowed into fewer and fewer lines. Power plants then began shutting down to avoid the damage that would have been caused by the surge. Other plants tripped offline because transmission line failures left them with no output paths for their power. Within 7 minutes, the cascading failure had propagated across the entire region, shutting down 256 power plants and throwing 55 million people into darkness. Well, recovery efforts began immediately, and power was restored to some areas that evening, but it took 4 days to bring the entire system back online. During this period, several people died from carbon monoxide poisoning caused by the portable generators they were using for backup power. Many water supply systems shut down for lack of electricity to run their pumps, and the resulting loss of system pressure caused contamination of water supplies, triggering boil water alerts in several cities. The shutdown of wastewater pumps caused several major sewage spills into waterways. Commuter and intercity rail lines shut down because their electric locomotives wouldn't run. Untold amounts of food spoiled due to lack of refrigeration. People sweltered in the August heat, having lost their air conditioning. Many of us took to our cars, if only for some relief from the heat. But relief was short-lived as non-operational signal lights caused traffic jams and gas stations couldn't run their pumps. Many airports were shut down because air traffic control, security screening, and ticket management systems couldn't operate. Several East Coast oil refineries were forced to shut down, triggering an increase in gasoline prices a few weeks later. Many cellular phone service providers remained operational until their backup generators ran out of fuel. But it didn't really matter because we couldn't charge our phones anyway. The only major infrastructure system that remained operational through the crisis was the plain old telephone service. But many consumers couldn't use it anyway because their cordless phones had no power. So, in considering the great Northeast blackout of 2003, we should reflect on 3 important questions. 1, what was the fundamental cause of this historic crisis? 2, what should be done to prevent it from happening again? And 3, what can we learn about everyday engineering from this event? Now, in response to the first question, the immediate causes are fairly obvious. The regional utility company failed to prune trees along the routes of its transmission lines. And a software bug deprived the system operators of situational awareness during the critical hour between the first local transmission line failure and the subsequent cascading collapse of the regional grid. Yet there does seem to be a more fundamental issue here. On a given day, somewhere within a system as vast and complex as a regional power grid, computer glitches, human errors, and isolated component failures are quite likely, if not inevitable. When these local failures happen, they ought not bring down the entire system. Thus, an important underlying cause of the blackout was lack of resilience, the grid's inability to accommodate a local failure. Now, the grid is designed to be resilient, but in this case, it wasn't, at least in part because it was loaded close to its capacity in the northern Ohio region where the cascading failure began. Thus, logically, there are three general strategies that might be pursued to lessen the likelihood of similar events occurring in the future. First, improve the grid's resilience by enhancing its monitoring and control functions. Second, increase power generation capacity. And third, decrease consumption. Now, the first of these solutions is already in the works. It's called the Smart Grid, an initiative of the U.S. Department of Energy that promises to improve the efficiency and reliability of our power generation, transmission, and distribution systems through enhanced monitoring and control. A severe limitation of our current system is that grid operators have no way of monitoring real-time energy consumption at its point of use. That meter mounted on your house measures consumption, but it doesn't talk to the power company. The smart grid will use sensors, two-way digital communications, and sophisticated computer tools to paint a fuller picture of real-time system status, to provide improved fault detection and self-healing without human intervention, capabilities aimed at preventing large-scale failures like the Great Northeast Regional Blackout of 2003. Smart grid technology is also being designed to accommodate the highly variable power inputs from an increasing number of renewable generation systems, and it will even permit consumer devices inside the home to respond to the current state of the grid. For example, an air conditioning system might shut itself off when the cost of power exceeds a certain threshold. Now, this is exciting stuff that you'll be hearing a lot more about in the years ahead. Stay tuned. The second potential solution, increasing power generation capacity, is particularly challenging in an era when so many high-capacity coal-fired power plants are being shut down because of their inability to meet federal emission control standards. In the short term, new natural gas-fired generating facilities are bridging this gap. But the natural gas boom can't last forever. Thus, over the long term, our ability to continue generating enough power to meet our needs will depend on continued expansion of renewables, primarily solar, wind, and geothermal. It's worth noting that the 2003 blackout began in mid-afternoon on a hot summer day, precisely the conditions under which photovoltaics can be expected to deliver maximum power output. There's great potential for this technology to relieve strain on the grid during the periods when we need it most. Clearly, though, increased capacity won't solve the problem over the long term if we don't also curb our seemingly insatiable appetite for energy. Throughout this course, we've seen many examples of technologies and design approaches that can achieve substantial reductions in energy consumption. But actually achieving these reductions will require not just technology, but also a broad societal commitment to sustainability. And finally, what can the Great Northeast Blackout of 2003 teach us about the world of everyday engineering? I'll highlight three lessons I find most compelling. First, the blackout and its aftermath vividly illustrate the interconnectedness of the technologies that constitute our civil infrastructure. A localized failure of several power transmission lines in Ohio led to a major regional collapse of power generation, transmission, and distribution, which then precipitated major failures of water distribution, wastewater treatment, cell phone networks, refrigeration, air conditioning, traffic control systems, railroads, airports, and oil refineries. The list of system failures caused by the 2003 blackout looks astonishingly similar to the syllabus for this course. On August 14, 2003, the interconnectedness of our infrastructure was a liability. But on most other days, it's an awe-inspiring human achievement. evidence of the integrated efforts of engineers and builders representing a broad array of specialized disciplines, all working together to enhance the human condition. Second, the blackout and its aftermath remind us how much we depend on everyday technologies for our livelihoods and quality of life. I experienced the blackout myself and still vividly remember how disconcerted, disconnected, and unproductive everyone was until the lights came back on. Our challenge is to appreciate these technologies when they're working well, rather than only on the rare occasions when they fail. Third and most important, as you listen to my account of the 2003 Northeast blackout, I hope you discovered that you're able to understand the scientific issues underlying a technological failure of mind-boggling complexity, to see the intricate interconnections between the many technological systems affected by the failure, to discern its underlying cause, and to formulate a rational proposal to prevent its recurrence. If so, then you've achieved precisely what I hoped you'd gain from this course, and I fully expect that you're ready to apply your understanding of everyday engineering to the many technological issues that will cross your path in the future. Thank you. So how does this differential accommodate the significant, sorry, I knew that was going to happen. If the ground fault remains, the breaker trips again. No, not yet.